This is a short module on the concept. Visit mockat.com to access the complete concept video, practice questions, quiz of the day, and other free resources to start your prep right away.
Now, before we start with the concepts of this lesson, you need to understand that we'll be working in the positive integral world. So the numbers are going to be 1, 2, 3, 4 and so on. Starts with 1 and goes up to infinity. Alright, so before we proceed with the concepts, let's look at factors and multiples and what they mean. Factor of a number is any number which is going to perfectly divide a number. Right, so the factors of 12 are going to be 1, 2, 3, 4, 6 and 12. Multiples of 12 over here are going to be any number from this world if you take it and multiply with 12. Right, so we start with the smallest one, which is 1. You get 12, 24, 36 and so on till infinity. Multiples are going to be infinite, factors are finite, right? So these you can count, the number of factors will come to that. Now the smallest factor of a number is going to be 1, the largest factor is going to be the number itself, the smallest multiple is the number itself, the largest is going to be infinity, right? So the only factor which is also a multiple is the number itself, every other factor is going to be smaller than a multiple. Now the first concept of successive division using HCF, so this is only for HCF, right? When you have two large numbers like this, what you could do is take the larger number and divide it by the smaller number. Right, so 204 into 2 is going to give us 408 and we proceed with this. Right, so 24 is the remainder. Now the previous divisor becomes the dividend over here, 204. 24 tables will be useful. 8 into 24 is 192 and you have 12 left over here. We are not getting 0, so we proceed with this. 24 over here is going to come in here and 2 times 12 is 24. Here the remainder becomes 0. The HCF is going to be the last divisor over here. So the HCF in this case is going to be 12. Common division is a very commonly used method for finding HCF and LCM for relatively smaller numbers. So 24, 36 and 90. First up, to find the HCF, you can pick any large number which is divisible by, or rather which divides all three numbers over here. Right, so 6 we know does, and 6 4s are 24, 6 6 are 36 and 6 and 2, 15 is 90. Alright, so now we can't find any other number which is going to be perfectly dividing each of these. So we stop at this and we note the HCF over here, which is going to be 6. To find the LCM, we need to proceed, right? So we need to take two numbers at a time and see if any primes are going to be dividing them. From this point onwards, we work with only primes, right? So 2 over here perfectly divides these two, 4 and 6. So we get 2 and 3 over here. And 15, it doesn't, so we write 15 as it is. Next up, 3 over here is going to be divisible, right? Dividing. So we get 2, 1 and 5. Now we can't find any other number which is going to perfectly divide any two of these. So we stop at this. The product of all of these, right, is the LCM. So LCM over here is going to be 6 into 2 into 3, which is 36, into 2 into 5 over here, which is 10, and we get 360. A prime factorization method is generally used where you can prime factorize and write them at ease. Right, so the HCF of two of these numbers, let's say A and B over here, is going to be the smallest pars we have to take for each of the primes, right? So for 2, it's going to be, the smaller par is going to be 3. So 2 cube into, in the case of 3, it's going to be 4 into 5 par 4. The LCM in this case, we're going to take the larger pars, which are going to be 2 par 5 into 3 par 7 into 5 par 7. Now, when there are only two numbers over here, right? So only two numbers, the product of the two numbers, A into B, equals the HCF into LCM, because any one of these is going to contain the larger and the other is going to contain the smaller part, and they are all going to be used up in the HCF and LCM. If only in the case of HCF and LCM of two numbers does this rule apply. Now, if there are 3 or more numbers, this concept of finding the HCF and LCM will continue, which is to write the smallest pars in the case of HCF and the largest pars in the case of LCM. Right, so ABC over here, the HCF is going to be 2 par 3, which is the smallest par, into 3 par 4 into 5 par. The LCM over here is going to be 2 par 7 into 3 par 7 into 5 par 7. Now clearly the product of these two, HCF and LCM, is not going to be the product of all three of them or any two of them. So the condition of product of HCF and LCM being equal to the product of numbers will not apply when there are 3 or more terms involved. Now when it comes to HCF and LCM of fractions, right? So HCF of fractions is going to be the HCF of numerators divided by LCM of denominators. And when it comes to the LCM, it's going to be the opposite, right? LCM of fractions over here is going to be LCM of numerators. Whatever you're applying over here, that will continue with the numerators. For the denominators, the opposite will be the case. That is HCF of denominators over here. Now to find the number of factors, which I've said is going to be finite. So if the number is going to be equal to A par P into B par Q, into C bar R, where A, B and C have to be primes, right? R primes. This can in fact continue over here, right? So they are all going to be primes. Then the number of factors over here is going to be equal to P plus 1 into Q plus 1 into R plus 1 and so on. So if we take the number 60 for instance, 60 can be written as 2 square into 3 power 1 into 5 power 1, right? Prime factorized form. The total factors over here is going to be the power plus 1, 3 into, the next two powers are 1 and 1, so it's going to be 2 into 2 over here. It's a total of 12 factors. Now if you need to manually find it, I've told you that 60 equals, you have to write it as 1 into which number? 60 itself. Then pick the next smallest factor. It's going to be 2 into 30. And keep finding factors between these two, right? So 3 into 20, 4 into 15, 5 into 12, and finally 6 into 10. You can't find any other factor between these two and you stop at this. These over here are your 12 factors. To find the number of odd factors, ignore 2 square over here, which is what makes it even, right? 3 power 1 into 5 power 1. Number of factors over there is going to be 2 into 2, which comes to 4. To find the number of even factors, you just need to subtract the odd factors from the total factors and you get 8 even factors in this case. Note that any number will have at least one odd factor because 1 itself, the smallest factor of the number, is odd. Even factors, you can have none of them as well, right? For odd numbers, you'll have 0 even factors. Now, before we move to point 8, you need to understand that a perfect square is going to have odd number of total factors, right? Total factors over here is going to be 3 into 3, power plus 1 into power plus 1. That's going to be 9. Any number that is not a perfect square is going to definitely have even number of total factors. That's because one of the parts is going to be odd, right? So power plus 1 will make it an even number. In this case, it's 4 into 2, which equals 8. So if a number is said to have an odd number of total factors, then that number is definitely a perfect square. Now the 8th condition is where the factors are going to be perfect squares or perfect cubes, right? So let's take a number which is going to be 2 power 7 into 3 power 8 into 5 power 13. The number of perfect square factors over here are going to be, I have to write this as 2 square to the power of something, right? How many 2 squares are there? There are 3 of them. Number of 3 squares over here is 4. The number of 5 squares over here, which is available, is 6 of them. So once you write it this way, the number of perfect square factors is going to be the power plus 1 into power plus 1 right now. So it's going to be 4 into 5 into 7, which comes to 140. For perfect cube factors, likewise, we have to write it as 2 cubed to the power of something, in this case whole square, 3 cube. From the 8, we can use only 6 of them. And for 5 cube, we have 4 such 5 cubes available. Right, so once again we apply the formula, so power plus 1 into power plus 1, so 3 into 3 into 5, and that gives us 45. Therefore 140 factors of n over here, the number, are perfect squares, and 45 factors of the number are perfect cubes. Now on to expressing numbers as product of two numbers, right? So for this we have to first prime factorize 36, we get 2 square into 3 square over here. Then we'll have to find the number of total factors. Total factors in this case is going to be 3 into 3, which is 9. Likewise, for 48 over here, we get 2 power 4 into 3, and total factors in this case is going to be 5 into 2, which is 10. Now, where it's even number of total factors, the number of ways in which you can write as product of two natural numbers is very simple. It's going to be the total factors by 2, right? So in this case, it's going to give us 5. Now, where it's going to be odd, then if it's going to be the product of two natural numbers only, then we have to do total factors plus 1 by 2, because the last is going to be 6 into 6, right? Because it's a perfect square. We have to count only 1 6. So in this case, it's going to be 9 plus 1 by 2, which gives us 5 as well. Whereas if it's going to be, the question is going to be product of two different natural numbers, or the natural number should be different, the last case of 6 into 6 should not be counted. So the answer over here would become TF, total factors minus 1 by 2. You have to subtract the last case, and you get 4 such ways of expressing it as product of two different natural numbers. Now, if you're asked to find the product of all the factors of these two numbers, once again, prime factorize and find the total factors. Once you found the total factors, here, whether it's odd number of factors or even number of factors, doesn't matter. The product of all the factors is the number to the power of total factors by 2, 9 by 2 over here. Likewise, in this case, it's going to be 48 to the power of 10 by 2, which is 5. Do not worry about this by 2 over here. The square root, it will turn into, and root of 36 is going to be a rational number, or because 36 over here is a perfect square, and that is why you had odd number of factors. This will be taken care of. Now onto the basics of remainders. A remainder is something which is left over after a division, right? So if you divide a number, let's say 17 by 5, 3 times 5 over here is going to give us 15, and the remainder over here is 2. The number can be recreated this way, right? So this is the number, this is the divisor, and this is the quotient over here, and the remainder. It's d into q, divisor into quotient, plus the remainder, right? So in other terms, if you have a certain number of blocks over here, let's say 17 blocks, if you want to keep removing 5, right? Division over here is nothing but repeated subtraction. Remove 5 blocks at a time, right? So 5, 5, and 5 you remove. You're left with 2 blocks, but you're allowed to remove only 5 at a time. This leftover number of blocks over here is the remainder, which you're not able to remove with your divisor. Now for later concepts in this lesson, we would be using negative remainders as well, which means we would continue to remove 5 from 2 as well, and we'd be left with a remainder of minus 3, right? So get comfortable with that. You can keep adding how many of divisors you want or remove how many of divisors you want. But the remainder over here for this particular number will remain unchanged. So 217, if you add some multiple of the divisor, let's say 25, and it becomes 42, even then if you're going to be dividing it by 5, the remainder will continue to be 2. Now on to using HCF when it comes to remainders, right? There are 2 concepts over here. One where the remainders are provided to us, the second where the remainders aren't. Start with the first one. Here you'd be given the numbers 100, 125, 150 and 200, and when divided by the same number n, some number n, the remainders are going to be 4, 5, 6 and 8 over here. These are your remainders and these are your number, right? So if you subtract the remainder from here, you're going to get the dq, because the numbers in the format of dq plus r. So subtract these and you get 96, 120, 144 and 192. Now the largest possible value of n in this case is actually the divisor, right? The largest possible value of the divisor is going to be, these are all multiples of the divisor, right? So some divisor which should be perfectly divisible by all 4 of them. That's the highest common factor. The HCF of these 4 values, right? These 4 values is going to give us 24. So n equals 24 in this case. Now if you're asked to find all possible values that n can take, right? So then you'll have to write 24 as 1 into 24, 2 into 12, 3 into 8 and 4 into 6, and then see which of these numbers can be your factors. A general tendency will be to mark all of them, right? So mark all of them, but you cannot do it in this case, because if you're dividing by 3, for instance, you can't get a remainder of 8. Your remainder is always going to be less than the divisor. So in this particular case, there are 2 values which your n can take. They are 24 and 12. Now 8 also cannot be a divisor, because when you divide by 8, your remainder cannot be 8. It has to be less than that. The next concept is to find the largest positive integer that divides 88, 39, 102 and 60 and leaves the same remainder over here, right? So you have to first write them down in ascending order, right? So 39, 60, 88 and 102. Now where we do not know the remainder, but we know that it's going to be the same, right? To find the largest integer which divides it, you need to understand that the remainder will continue to be the same if you keep adding a certain number of divisors. Right, so what did you add to 39 to get 60? That's the difference between it, which is 21. Over here it was 28 and over here it was 14. So as these are all supposed to be multiples of your divisor, the HCF of these 3 numbers over here, is going to give us 7, which is going to be the largest positive integer that divides all 4 of them. Now to the LCM concepts of the remainders. There are 3 concepts over here. The third being the Chinese remainder, which we'll look at as well. We'll start with the first 2. The first is where you have the same remainder which is left over. In this case, you're going to be given the divisors and you'll have to find the natural numbers or the dividend over here. Right. So what is the third smallest natural number that leaves the remainder of 1 when divided by 2, 3 and 5? Now over here, if you're going to have the same remainder, the number format is going to be the LCM of the divisors over here, 2, 3 and 5 into k plus the remainder which was 1. The LCM of these is going to be 30. So 30k plus 1 is the number format. So the smallest natural number would have been 30 into 0 plus 1. Right. So that's the smallest. We are asked to find the third smallest. So 30 into 1 plus 1 is the next. And 30 into 2 plus 1 is going to be 61, which is your third smallest natural number. Now the second case is going to be where we have the same negative remainders. Right. For that, we first have to write down the divisors over here, which are going to be 24, 36 and 48. And then the remainders 11, 23 and 35. And here if you once again subtract the divisor from this positive remainder, we get a negative remainder which continues as the remainder, right, which is going to be 11 minus 24, which is minus 13, 23 minus 36, which is minus 13, and minus 13 again. Once again, we have the same negative remainder in all three cases. The same case as the last one will apply over here. So the number format is going to be, right, so n equals LCM of 24, 36 and 48 into k minus 13, right? So what was the negative remainder you put over here? And this over here, the LCM is going to give us 144k minus 13. We are asked to find the smallest number over here. We can't start with 0 because that will give us minus 13. So we start with 1. K equals 1 if you substitute. Then 144 minus 13 would give us 131. Now the third case with LCM concepts with remainders involves Chinese remainder over here. Right, so what is the smallest number that leaves remainders of 1 and 6 when divided by 3 and 14? Now, the positive remainders are different. The negative remainders are also going to be different because 1 minus 3 is minus 2, 6 minus 14 is minus 8. Minus 2 and minus 8 are not the same. So, in which case, you'll have to apply Chinese remainder. So, n equals the number format you have to write. When divided by 3, remainder is 1. So, it's in the 3a plus 1 format. Divided by 14, remainder is 6. It's going to be in the 14b plus 6 format. Now keep the variable with the smaller coefficient on one side and move everything else to the other. We get 14b plus 5 divided by 3. Next step to simplify and to make our iterations easy, what you can do over here is these coefficients you can divide by 3 and write down the remainders. 14 by 3, the remainder is 2. So 2b plus 5 by 3, the remainder is 2 once again by 3. Now what is the smallest value of b, which would ensure that 2b plus 2 is going to be perfectly divisible by 3, right? So we have to start substituting values into b from 0 onwards and not from 1. That you need to be careful with. B equals 0 will give us 2 by 3, it's not divisible. B equals 1 is going to give us 4 by 3, which also is not divisible. B equals 2 is going to satisfy, right? So because we get 6 by 3 over here. Now b equals 2 has to be plugged into this value over here to find the smallest number. The smallest number is going to be 2 into 14, 28 plus 6, which is 34. Right, so 34 when divided by 3 leaves a remainder of 1 and divided by 14 leaves a remainder of 6. Now that you found the smallest one, the practice we followed for the previous ones will continue, which is the LCM of the divisors of 3 and 14, right, which is 42 into k or c or any variable you can take. 42k plus 34 is the number format which satisfies these conditions. So 42k plus 34 is the number format which satisfies these conditions. Now to successive division with remainders, what are the smallest and fourth smallest natural numbers that leave remainders of 1, 3 and 2? Write it in the bottom, right? So these are your remainders and the divisors you write in the top. It's going to be 3, 4 and 6 respectively, right? Successive division is what is happening over here. So ignore the top right divisor, right? From the bottom right remainder, you go up diagonally and you come down and then go up diagonally and come down. As you go up, you multiply. As you come down, you add. So 2 into 4 is 8, 8 plus 3 is 11, 11 to 3 is 33, 33 plus 1 will give us 34. So 34 over here is the smallest number which satisfies this, right? So there is a number format for this as well. In this case, we do not take the LCM, we take the product of the divisors, right? You have to multiply all of them and not take the LCM. 6 4s are 24, into 3 is 72. So the number format over here is 72a plus 34. Now, for the smallest natural number, we took a as 0, right? Smallest was 72 into 0 plus 34, which is 34 itself. In the case of the fourth smallest, it's going to be 72 into 3 plus 34, which comes to 250. Now to sum of remainders. For sum of remainders, you don't need to add all of them and then divide by 4 and find it, right? So you can individually find the remainders and then add them up, right? 3 for the remainder when divided by 4, the last 2 digits is what matters. You would have seen it in the divisibility lesson. 86 by 4, the remainder is 2, plus 75 by 4, the remainder is 3, 45 by 4, the remainder is 1, 2 plus 3 plus 1, 6 by 4, the remainder is 2. In the case of product of remainders, likewise, what you can do is individually divide and write down the remainders and multiply them. 234 by 5, remainder is 4. The last digit is what matters, as you've seen in the divisibility lesson. 6 by 5, remainder is 1, 8 by 5, remainder is 3. Divided by 5. So 4 into 1 into 3 is 12. Right? So 12 by 5, the remainder is going to be 2. Now on to remainders with exponents. Remainder of 70 power 795 divided by 23. What you can do is divide the base by the divisor directly. right? 70 by 23 over here leaves a remainder of 1. Remainder is what you're focused on. 1 power 795 divided by 23. The remainder will continue to be 1. Another example for remainder with exponents, alright, so the remainder of 15 power 125 over here divided by 8, alright, so divide by 8, I'm going to divide the base by 8, I'm just writing it this way, right, and what do I get over here as the remainder? I get 7, but 7 is very close to 8, it's just 1 less than 8, so I can take the negative remainder, right, so 15 by 8, 2 times if you subtract 8, you're going to get minus 1 over here as the negative remainder to the power of 125 by 8, minus 1. Power 125 is minus 1, so minus 1 by 8 over here. Now you can add back the divisor, you do a plus 8 over here and you get a remainder of 7. Now on to Eulers Torsion over here. The formula for Eulers Torsion is simple, right? So this is going to be the number itself into 1 minus 1 divided by the first prime factor into 1 minus 1 divided by the second prime factor and so on. Even if you're going to have numbers like 2 power 57 into 3 power 46, there are only 2 prime factors over here, 2 and 3. You're not going to consider the powers over here, right? So A and B are going to just be 2 and 3 if the number is going to be this. So therefore, when the number is 24, we know that the only 2 prime factors over here are 2 and 3, right? The power of 2 does not matter. Therefore, the Eulers Torsion, this is the symbol which is used for that, is going to be 24 into 1 minus 1 by 2 into 1 minus 1 by 3 over here, which is 24 into half into 2 by 3, right? And we get 8 over here. Right, so therefore there are 8 natural numbers which are less than 24 which are co-prime with it. Co-prime means the HCF of 24 and the numbers, the 8 numbers which are less than it is going to be 1. Also to be noted over here for you is the Eulers Torsion of any prime number is going to be 1 less than it, because all numbers less than 7 are going to be, or any prime number is going to be co-prime with it. Alright, so of 37 you can directly write it as 36. Or even if you apply the formula, you'll get the same result. Now, its application when it comes to Fermat's little theorem is very important, right? That of Eulers Torsion. Now, the remainder of 79 to the power of 1983 divided by 12, right? So you can apply that directly only if a condition is satisfied. That is 79 and 12. These two are going to be co-prime, which is the case because 79 over here is a prime number. So given that these two are co-prime, you can continue to apply exponent rule, that is to divide the base by this divisor. But now when it comes to the power can be divided by the Eulers Torsion of 12. Right? So Eulers Torsion of 12 over here is going to be 12 into, the two factors are going to be 2 and 3. Therefore 1 minus half, which is half, and 1 minus 1 by 3, which is 2 by 3 over here. And 2 into 3 is 6. Right? So you get 2 over here and you get 4 as the Eulers Torsion of 12. Therefore, this power over here, you can divide by 4 and continue to write the remainders because it's all about the remainders. 79 by 12, 12, 6 are 72, so you get 7 over here. 1983 by 4, you want the remainder. Alright, so divisibility once again by 4, 83. Only the last 2 digits divided by 4, you need to write the remainder, which is 3 in this case, 83 by 4. Divided by 12, 7 cubed is 343. 343 by 12 over here, you can just divide it and write down the remainder. Now, so 12 2s are 24, you're left with 103, and 12 into 8 is 96, 103 minus 96 is 7. 7 is the answer over here. Now the base and divisor are not co-prime, right? So not very expected in your exams because it's a little cumbersome. So 250 power 340, and even if they do turn up, these shouldn't be the first ones you should attempt. By 44 over here, 250 and 44 are not co-prime, so therefore you'll have to prime factorize 44. 44 is nothing but 2 square into 11, right? So divided by 2 square, see as to what your remainder is going to be. It's going to be 0 over here because 250 contains a 2 and 2 power 340 is going to be perfectly divisible by 2 square. So over here the number format is going to be when divided by 4, the remainder is 0. So 4a plus 0 or simply 4a over here is the number format. Next up, when you divide 250 power 340 over here, right? So by 11, right, which is the other number, then what is your remainder going to be? The base over here, you can divide by 11 itself. The power by the Eulers Torsion of 11, which is 10. Right, so 10 over here. 340 by 10, the remainder is going to be 0. 250 by 11, you needn't even write it over here because anything to the power of 0, you're going to get a remainder of 1 over here. Now for the sake of continuity, I'll just write it as 8 over here. 8 power 0 divided by 11. Now a number when divided by 11 leaves the remainder of 1. So the number format over here is going to be 11b plus 1. So you have to rewrite this as 4a equals 11b plus 1 because the numbers in both these formats over here. Now we can apply Chinese remainder and try to find the smallest value which satisfies. So A over here is going to be 11b plus 1 by 4. In fact, you can directly note over here that b equals 1 is going to give you 12 over here, which is perfectly divisible by 4. So b equals 1 has to be plugged into this, and you get n equals 12 over here is a multiple of 4 and leaves a remainder of 1 when divided by 11. Now this number format is going to be LCM of these two divisors, 4 and 11. So you get 44c plus 12. So 44c plus 12 when divided by 44 will leave a remainder of 12. So the answer over here is 12. Now on to writing a number as a difference of squares of positive integers, right? So the catch over here is this: if the number is going to be in the 4a plus 2 format, that is, it is divisible by 2 but not 4, then the number of ways in which you can write this as difference of squares of two positive integers is 0. So now you get two scenarios over here. One is where the number is odd, the other is where the number is in the 4k format, right? So it's a 4 multiple. Now if it's going to be odd, you find the total factors of the number itself. And once you found the total factors, TF by 2 over here. If it's an even number of total factors, even TF. And if it's going to be an odd number of total factors, right, which is going to be the case if the number is a perfect square, it's going to be TF minus 1 by 2, because you'll have to remove the case where it can be 0, right? If it's a perfect square, then for instance, let's say 36, 6 square minus 0 square case should be removed, because you have to write it as difference of squares of two positive integers over here. Now, if it is in the 4k format, you'll have to find the total factors of n by 4, right? So once you've found that, then once again, depending on whether it's going to be even total factors or total factors, you continue with this. Now, in this example over here, 48 is an even number and it is a multiple of 4. So first up, we divide 48 by 4 and we get 12, right? So the total factors of 12 over here, and 12 is nothing but 2 square into 3. This is going to be the power plus 1 into the next power plus 1. So that's a total of 6 factors. So this total factors by 2, which is 6 by 2, equals 3. There are 3 ways of writing 48 as difference of squares of positive integers. Now the next concept is relatively simple to remember. Sum of 2 or more consecutive natural numbers, right? The number of ways in which you can write a number. Let's say 60 over here is the number. Number of ways you can write it as sum of 2 or more consecutive natural number is the number of odd factors minus 1. So 60, for instance, prime factorize it, 2 square into 3 into 5. The number of odd factors over here is going to be, ignore the 2 square over here, power plus 1 into power plus 1, so it's 2 into 2. And then subtract a 1, because the smallest odd factor of 1 should not be considered, because it has to be the sum of 2 or more consecutive natural numbers. So 4 minus 1 and we get 3. So 3 is the answer for this. Next up is remainder theorem for algebraic expressions. What is the remainder when this is divided by x plus 3? Right, so you'll have to take this in the x minus a form. So where a polynomial is divided by x minus a, the remainder is going to be f of a, right? So if this over here is f of x, this one. Now, so f of a over here is nothing but f of minus 3, right? So if x plus 3 is x minus a, f of a is f of minus 3. So minus 3 over here has to be plugged into x over here, and we get minus 3 power 4, which is 81. Minus 3 cube is minus 27 into minus 3, which gives us plus 81. Minus 3 square is plus 9, and you get a plus 18 and then a minus 8 over here. 81 plus 81 is 162, plus a 10 will give us 172. Now we need to note that for certain x values over here, this polynomial is going to be perfectly divisible by x plus 3, and the x values are going to be such that 172 over here will have to be perfectly divisible by x plus 3. For instance, over here, this is going to be perfectly divisible by 4. So if x is 1, then 172, or rather this polynomial, will perfectly be divisible by x plus 3. Or even if x is going to be 169 over here, 169 plus 3 is 172, it will be perfectly divisible. Next up is Wilson's theorem. The remainder when n minus 2 factorial, that is 35 factorial, is divided by n, right, where n is prime number, 37 is a prime number over here, the remainder is always going to be 1. Now the remainder when n minus 1 factorial, or 36 factorial, is divided by 37, which is a prime number, the remainder over here is going to be 36 into this one, which is 36. Therefore, remainder when n minus 2 whole factorial is divided by n is going to be 1. The remainder when n minus 1 factorial divided by n is going to be n minus 1 itself, where n is a prime number. So that was Wilson's theorem. Lastly, remainder when terms are in GP. What is the remainder when 2 power 1 plus 2 square plus 2 cube and so on till 2 power 63 is divided by 5 over here? For this, what you need to do is start writing the 2 powers over here, starting with 2 power 0, that equals 1. 2 power 1 is 2, 2 square is 4, and we stop at this because these are the numbers less than 5. Any 2 or 3 of these numbers will add up to 5, you've got to look for, and you notice that 1 and 4 over here add up to 5. So if you arrange these in order, right, starting with 2 power 1, let us say, right, 2 power 1 plus 2 square plus 2 cube plus 2 power 4, you would note that the first and the third, right, so this plus this is going to be divisible by 5. Likewise, next two numbers over here, set of numbers with a gap of 1 are going to be divisible by 5. The reason is simple. For instance, if you have 2 power 37 plus 2 power 39 over here, you can get a 2 power 37 common, you get a 2 power 0 plus 2 square, which gives you 5. Therefore, every set of 4 numbers over here can be removed. We have a total of 63. Instead of removing 4 from the start, we can remove 4 from the end, right? If you keep removing 4 terms from 63, you're left with the first 3 terms. 63 by 4, the remainder is 3. Therefore, 2 power 1 plus 2 square plus 2 cube is left over. The remainder of this divided by 5 is going to be your final remainder, because the rest of them would have been divisible, perfectly divisible by 5. Once again, 2 power 1 and 2 power 3 you have over here. That's going to be divisible by 5. 2 square by 5, remainder is 4. So these are your concepts for factors and remainders.
If you found this video useful, please like and share it. Subscribe to the channel and let us know what you'd like to watch next in the comments below. Don't forget to visit Mockat.com to access free resources to get through your Dream B School.